Thanks everyone for joining and for showing up. And thanks Dr. Aritran Piplai and Dr. Sudeep Mittal. So Dr. Sudeep Mittal, you all pretty much know him. He is an assistant professor in our department, majoring in cybersecurity and AI. So he will be introducing with Dr. Aritran Piplai. He is an assistant professor at University of Texas at El Paso. So please welcome him, and he will be. I hope you had a great session. Thanks for showing up. Over to you, Dr. Mittal.
Oh, yeah. Thank you, Shashwata. Thank you, everybody from the AI Club for organizing this and inviting Dr. Piplai. So Dr. Piplai is an assistant professor at University of Texas, El Paso. He got his PhD in computer science at University of Maryland, Baltimore County. He has published in multiple top tier conferences and journals, and has reviewed multiple papers and conferences like EMNLP, AAAI, and CCS. So I've known Dr. Piplai and his work for a long time, and I thought that this would be a great chance for him to communicate some of the work that he's doing to you all. So I think Dr. Piplai can start the presentation.
Okay, thanks a lot for the introduction. Hope you all can hear me. Yeah, let me know if you can't. So just like Dr. Mittal was saying, my research area, like I have been publishing in a lot of conferences in AI and cybersecurity because that happens to be my research area. Specifically, I work on cyber threat intelligence, reinforcement learning. Recently, I've been looking at meta learning as well. And in the area of cyber threat intelligence, I'm also looking at large language models. So today's talk is very specific. It's about modeling cyber attacks and defenses with semantic knowledge. And specifically, we will be looking at some reinforcement learning algorithms and how they can benefit from the use of external knowledge. What we know about the current state of the art in machine learning, and if you talk to anyone in the community, you would most likely hear the same thing, that a lot of these machine learning models that people deploy at these big organizations, they don't work well for evolving threats. So what that means is you train the model with some historical data, and even if you have a rule-based system, it doesn't need to be a machine learning system, but even if it's a rule-based system, it looks at past incidents, it derives some signatures by itself, and then it tries to detect some cyber attacks. Now that always doesn't work in the terms of malware or cyber attacks because it's always evolving. So historically derived signatures and attack patterns or historically derived models are not so great when you want to detect unseen attacks, which is similar to the second problem that a lot of people would say that you can't have a model which generalizes well. So if you build a model which sort of generalizes well, if you're lucky enough to build a model which generalizes well across different threat patterns, you're most likely going to end up with something which will have a very high false positive rate. Different cyber attacks have different indicators, different parameters, different things that you as an analyst should be looking at when you want to identify whether this is a cyber attack or not. And this changes widely when there's a new type of attack that's coming up. And also the last thing is it's not very interpretive. Whenever you create a machine learning model, which is sort of a black box in nature, the way it reaches conclusions and decisions is widely different from what an analyst would do at that point. So for instance, if you ask someone that this is my training data and this is my label for malware or benign or cyber attack or normal traffic, they are most likely, the model is going to learn something which is going to be so confusing that if you show that to, even if you build an XAI system, you would end up with some set of rules which are very complicated and which is not something that a human would come up by his or herself. Now, what do we do in these situations? So clearly, you cannot expect to have the malware or cyber attack samples beforehand because it's changing so much. What typically happens is there are some organizations which will hold this malware and some actual traffic, and then they are not supposed to disseminate that into the general public, but they will give you some sort of information from where you can infer something, which in turn would be helpful for downstream machine learning models. So what do these things look like? So this is what like cyber threat intelligence helps us here, because this is, for instance, is an after action report. So they take samples from the wild, detonate them in an isolated environment, and then they analyze them and then disseminate the findings of that experiment to the general public. So over here, you can see a particular after action report, which is describing a particular malware, which is from a particular campaign called Nikon. And what we have done here is we are looking at specific terms or specific expressions of interest, which will help us describe this malware. So this is something that you as a practitioner would do, that you would devise a particular system which is going to extract some key information which you would find helpful in describing a malware. And the way we do this is we employ some of the existing methods of named entity recognition and relationship extraction, where we extract key information about cyber threats or malware, and then we try to establish how those things are related to each other. So over here we can see that it's an icon, which is a campaign, and it's using some spearfish documents. It's mapped to some existing vulnerabilities that we know of, and it's using a suspicious email to deploy the payload. Now, all this information is super helpful if you do not have the sample for a malware that belongs to this particular group. Now, how do we do this? We have a numerous bunch of data sources which can describe different malware families or different parts of a malware. We extract these key information or key pieces of information of interest, which will help us describe this. Now, what are we looking at? That's actually something which domain experts would be able to do. So if you're really interested in cybersecurity, you should be able to tell what information should I be looking at in an open source text, which will help me describe a particular malware or any cyber attack, for instance. Now we extract these entities, and then we try to extract some relationship about how those entities are related to each other. And in the end, we end up with a graph structure, which we call the cybersecurity knowledge graph, which helps us describe particular pieces of cyber attacks and particular pieces of malware. Now, if you are lucky enough to have the sample with you, you can actually detonate the sample by yourself, extract the behavior of the system or the behavior of the malware, and fuse them with whatever you have learned from textual descriptions of this cyber attack or malware. Now, this is something that you would do if you had the sample, but even if you didn't have the sample, you would still have a system which can give you some important information which will help you understand what the malware would do even without the existence of a sample. Now, this always comes with some risks. Because we are mining information from open source text, it has some caveats. So this is one research that we did before, that if there is a bad actor who knows about this kind of a system, that you are extracting information from open source text, the bad actor might be able to fool you by generating fake intelligence, which looks exactly like a cyber threat intelligence from where people usually mine this information, but they contain incorrect information, which can actually lead you to misleading inferences. So if you look at this architecture, this is a GPT architecture that we used to generate fake cyber threat intelligence. And it's quite surprising, because when we actually asked industry experts or people who are experts in this field, that can you tell a real cyber threat intelligence piece than something which is artificially generated, which contains incorrect information. Now, a lot of people were not able to tell, even though they were very accomplished in this particular field. Now, a particular defense mechanism which we developed after going through this is using graph neural networks. And how that would work is, let's say that you pass in a legitimate cyber threat intelligence, and then you create this graph-like structure, which is the cybersecurity knowledge graph, and then you pass another source of information which contains incorrect information about the same malware. So you look at existing or neighboring entities and then try to find out contradictions from which you should be able to tell how much should you trust this existing information that came from this new source. Now that can be automated a lot in a lot way with the help of graph CNNs, where the image structure is actually in the form of entities connected to each other in a graphical fashion, and then you apply convolution layers, and then you end up with a score which helps you filter out a lot of these triples or entity pairs which may be considered incorrect. So it's a form of consistency checking, and then it gives you a score. It's sort of like a regression model. And then if you filter on top of this score, you should be able to get exactly the high trust or highly reliable information that describes a cyber attack. Now, once we have this, we kind of reasonably can say that, okay, like we have a system which can have a reliable description about cyber attacks and malware in general. Now, what do we do with this information? So let's say that you are a bad actor, and this is from the perspective of bad actor. We'll hear about perspectives from the defenders as well. So let's say that you are a bad actor and you are using a malware which from the Nikon group. Now, you know that this particular malware has these capabilities of exploiting some vulnerabilities which could be mapped to some weaknesses identified here. So one of these weaknesses is CWE20, which utilizes DOS, and then it can also be triggered by improper input validation. Now, with this information, there are two things that that this malware could do. It could try out a lot of these vulnerabilities that it can exploit, or if it has some knowledge that there is this particular program which is defending this organization's network, and this has a vulnerability which could be exploited by this bad actor. Now, if that happens, then the malware does not need to try out all of the other weaknesses. It knows that there is a particular weakness that is 100% effective under these circumstances. Now, if that is the case, then the malware will perform this action, and then the program will crash if it has this particular weakness, and then it will gain access to the network's computers. So the reason why I'm telling you this is because I want to highlight that if you have partial information about something, you should not be required to exhaustively search for all the operations that you need to do to be successful in a particular task. Now, this is pretty common knowledge, but we will see how this could be applied in the setting of reinforcement learning and so on. Now, this actually, in the context of machine learning in general, can be thought of as the two different sources of knowledge. One is called the tacit knowledge, and one is called the explicit knowledge. So, for example, tacit knowledge is something that you understand by yourself. So if you are trying to teach someone how to ride a bike, there is no specific formula that you could actually feed that person, because the person has to try out a bunch of different things and then understand what is the best strategy for that person to ride the bike successfully. There is no rule book, no guidebook that can actually teach someone how to ride a bike. The person has to try it out by himself or herself. Now, explicit knowledge is something that is externally supplied to any agent. Now, what this explicit knowledge could look like is, let's say that you're trying to teach someone how to play chess, for instance. There is no need to try out a lot of different random actions, because there is a particular rule set that chess adheres by. If you have a chess game, there are some specific rules that the rookie goes in a particular direction, the queen goes in a particular direction. You should know that beforehand, before you are trying your hand at chess, because all the other random actions, like if you try to move the queen in a direction that the queen is not supposed to move into, that doesn't give you any insight about the game. So if you combine these two sets of knowledge, we find it extremely helpful in tasks like cybersecurity. So there is something that the model has to know by itself. There is no specific description, but there is also something that can be externally fed to the model, which can help the model reach decisions much better. So what this explicit knowledge looks like can be seen over here. It's actually a host of different sources from where we gather all this information. It could be a lot of these NOT and YARA rules. It could be behavior data from CVE, CWE. It could be some security bulletins. And the after action reports are also a good source of it. One example you saw a few slides back about the Nikon malware or Nikon cyber attack. So all these sources contribute to a very rich source of knowledge about existing cyber attacks. Now, it could help in situations where you don't actually know about a particular cyber attack. Let's say that you are a small company, you have trained your defenders with a lot of these data. However, you don't know about a particular malware family which has existed, which sort of emerged in some other country, let's say. And then you want to use this explicit information and feed it to your model so that the model, without having to see this particular sample which emerged somewhere else that your local company hasn't seen before, can use this information to update its defense. So the small company at this point doesn't need to wait to get attacked through this malware. It can just use this external knowledge, feed it to its system, and then update its system so that it can detect the cyber attack without having to see it. So we have built a lot of these models before, a lot of these knowledge graphs, which can capture this information really well. And it also has very strong reasoning capabilities. So if you have two different malware which shows the same pattern, you can actually infer that from the knowledge graph itself by querying over the knowledge graph. Now, this explicit AI needs to be provided to downstream machine learning tasks. And there is a strong motivation for it in the case of cybersecurity, which I hinted in a little bit earlier. So in AI for other domains, actually do not need a lot of information except for the data sample that it's currently looking at. So for example, if you're building some sort of a cat detector, I'm not entirely sure what the purpose for this would be, but let's say that you are. Let's say that you're building this cat detector and it's supposed to identify pictures of cats and it's supposed to distinguish this from pictures of other animals. Now, this looks like a fairly straightforward task. Cats have fairly distinctive features, and you are not required to explicitly define that you should be looking at these features when you're identifying cats. So no expert knowledge might be required to identify because the models right now are extremely strong. If they're exposed to a lot of these in training data, they should be able to infer these features by themselves. Now, if you look at what a security analyst looks at when trying to infer whether there's an attack, it looks something like this. It has a lot of these, let's say that you're looking at host information, the registry keys. You might be looking at packet level information. You might be looking at system behavior, like how the system attributes are changing. Now, with all these information, different malware attacks are, exemplified in like different ways. If you look at some can be captured through packet data, some can be identified through system behavior data, some can be identified by host information like registry key values, and some can be identified by a combination of all of them. So when you are dealing with and trying to detect something which requires a lot of these information, and it's also very transient, just because something works in this particular fashion right now doesn't mean that it will follow the same pattern later on. So for instance, if you build a cat detector now, 100 years later, you do not probably need to update your model because cats are not going to evolve as fast that it's going to look drastically different 100 years later. But if you're looking at trying to detect malware samples or cyber attacks, you need to update not even a year from now. You need to update every 3 to 4 months your entire model with the entire like 1 million or 20 million malware samples. That's what you need to do. Every 3-4 months, you need to have a very powerful server. You need to update that frequently every 3-4 months. And then you need to wait till you're attacked by some new malware samples and then collect that data, retrain your system, so on and so forth. So that's why only big companies can actually effectively do this. Small companies are still relying on rule-based systems. And that's exactly why we need this external knowledge source, because it helps you understand what you should be looking for, what parameters are good indicators for the presence of a cyber attack or a malware. However, we do not want to restrict our AI model to only look at these patterns which are suggested by external knowledge source. So that means if I know that there are certain types of cyber attacks which are present, and I know the existing signatures for them, if I provide those signatures to a particular model and expect them to only follow them, then we don't need the model. We can just rely on this external knowledge source to make these decisions by yourself. But the external knowledge source is also not exhaustive information. You need something that the model needs to uncover by itself. So that's why we need these exploratory options. And what we mean by that is we need to keep into account what this external world or the external knowledge is about this particular domain, but we also need to explore something which is unknown so that we can have the option of uncovering something which is not known. Now that brings us to the need for RL, and I want to demonstrate that through something that you might have seen. So this is a snapshot from the popular Netflix TV show Squid Game. What this is doing, like if you recall, I mean, most of you might recall this particular episode where the contestants were supposed to cross the bridge. This is a glass bridge. So on one side, I mean, some of these glass bridges are going to break if you stand on them. So they need to try out, jump on specific glass tiles. If it falls, you die. If it breaks, you fall and you die. If it doesn't break, you move on. And that is how the game was. Now there's only one thing that you could do at this point. You either jump on the tile. If the tile breaks, you're dead. If it doesn't break, you move ahead. Now there was one particular contestant who, for some reason, discovered some pattern into glass that will break, and discovered some pattern that the glass won't break, and was able to reach quite a distance based on that. Now that is what this external knowledge is. So you can try out different things. You can try out random actions, but at some point, if you're fed with some external information, you can make a more educated guess to reach a further distance. And this is what we are going to see in our reinforcement learning models, which is predominantly exploratory. That means it tries out different random actions in the beginning of its training phase. And then if you can feed it external knowledge, it can actually explore only certain actions or bias certain actions and still explore some unknown actions. So how do we design this reinforcement learning agents in the context of cybersecurity? So in reinforcement learning, you basically have the state, action, reward, and then the next state. The state could be something like the behavior of a system. So you're trying to understand if there is a malware based on the behavior of a system, or it could be nodes of a network structure where you're trying to model both attackers and defenders. The actions could be different. So in the case of detection, the actions could be what processes are being executed. So if you execute a particular process, what happens to the system parameters, and then you're trying to detect which of these processes is actually malicious. In the context of cyber attacks and defenses, you could be looking at some exploits that is being launched from one node to the other. And same with the defender, it could be looking at some defending actions or mitigation strategies that is being launched at a particular node or from a particular node to another. Now, what do we learn and what is the output of the reinforcement learning model? It's basically a policy, which is a probabilistic function. I mean, we are talking specifically about policy networks. There are other variations, but for the sake of this talk, we are focused on policy networks, which produces a policy signifying what is the probability that you take a certain action given a certain state. Now in this case, when we are modeling both cyber attacks and defenses simultaneously, it's kind of like what is the probability that a particular attacker action is to be taken given about the state description and given a defender action at the same time, and it's vice versa for the defender as well. So we are learning a probabilistic model. So for every single state that you enter into this policy, you should get a softmax output of the different actions that you can take at this particular state. Now, what we hope is that if you explore enough states and actions, you should be able to come up with a robust policy that should be able to give you the best possible action that you can take at a certain state. And if you sample from this strategy, you should be able to model even unseen threats as well. So notice that if you have certain states and actions, you can use that to train. But if you input another state that the model hasn't seen, it should be able to come up with another action which the model which should be good enough for that particular state. Now, how do we incorporate knowledge over here? We'll discuss that in a couple of slides. But what is an important motivation here is in the reinforcement learning, a lot of these episodes or iterations are in the training phase are guided by whether you are able to get a positive reward. So rewards actually guide reinforcement learning agents. So if in a particular iteration, you try out a bunch of different actions and then nothing really happens, you gain no knowledge, and you're basically cut off, and you try out another set of iterations almost instantly. Now, that is a big problem, and that's actually a big problem in reinforcement learning because a lot of these reward spaces are extremely sparse. That means in most of these episodes, you do not get any reward, and that means the model is not learning anything. Maybe in the first 10 or 15 iterations, it doesn't learn anything. You would be extremely lucky to find out some particular state for which you can get a reward. Now we try to improve that by giving partial rewards when you actually explore states which we know are beneficial for the attacker or defenders. For example, if you know that this particular cyber attack will show some indicator in the form of high network activity. So if the state changes and in a new state that you see network activity is rising, you associate a positive reward because it seems like you are exploring a particular state which might indicate the presence of the malware. So if you have denser reward spaces, you learn faster. It doesn't have to be exactly the same reward as you would get as detecting a malware or defeating the adversary. It could be some small partial rewards which will enrich your reward space. And if that happens, it can actually make the training way faster than traditional reinforcement learning with extremely sparse rewards in this case. Now, how do we incorporate this knowledge? Now, if you look at this graph, there is this knowledge graph at the center, which is guiding these agents with some information. Now, our knowledge graph contains both mitigation strategies and also indicators of attack, and also different attack patterns that cyber attacks have demonstrated before. So for example, if you describe a network structure where there is a particular node in the company which is using a Windows machine, and you want to gain access to a Linux server which is connected to a lot of other machines in the network, what you would do is you would actually feed a partial knowledge to the defender that the Windows machine accessing the Linux server needs additional protection. But the same knowledge could actually be used by the attacker as well. And the knowledge would be of the form that if you want to control the Linux server, you should first control the Windows machine that's accessing it, because that can give you some insight about how to control the Linux server. It can actually have some credentials exposed, or you can SSH into the Linux server and whatnot. Now, this is how we pass the knowledge, obviously not exactly in this natural language format. The knowledge graphs have this specific format in the form of semantic triples with which they hold information, and that can actually be translated to these attackers and defender agents while training these reinforcement learning models. Now, in order to do this, we did have to make a lot of these engineering contributions. So we had to develop this simulated network and cyber defense exercises. Now, a lot of these are typically done by humans. That means humans actually create these nodes, and then they actually say that these are the vulnerabilities of these nodes. And if you exploit this vulnerability, you are supposed to get this. However, we have this huge database of cybersecurity knowledge. We could actually leverage this information to describe all these nodes with some more modern information, that there are so many different nodes. For each specific node, these are the characteristics. So this is the operating system. These are the softwares that they're using. These are the known vulnerabilities of these. These are the known vulnerabilities of the software. And if you exploit this vulnerability, this is the kind of result that you can expect to have. Now, once you define this, you can start training your reinforcement learning model. And the way you do that is you simultaneously train an attacker and the defender. So the attacker performs an action, the defender performs an action, and then they jointly receive a reward. In our case, what we did was we tried to the reward were positive for the attacker and negative for the defender. So the goal for the defender would be to get the minimum reward, cumulative reward as possible, and a goal for the attacker would be to get the highest reward as possible. So specifically, we were giving 100 reward for successful exploit, a -100 for failed exploit, and 50 for discovering new nodes for the attacker's perspective. So the defender would actually get more rewards or more negative rewards if they were able to kick out the attacker from the network. So these are some examples of the action spaces that the attacker and defender were using. So the attacker would be launching a local exploit, would be launching a remote exploit, or once it has discovered a particular network node, it would be connecting to that node as well. The defender would have some very well-known functions to patch the system. Now, once we define this, we can come up with our own loss function or our objective function in this kind of scenario. So if you look at the left, it is the vanilla Q learning algorithm. So what we are trying to do here is we are trying to maximize the Q values for a particular state action sequence. And we are trying to ensure that it maximizes the cumulative future reward. So this is the QSA is basically the Q value, which tells you the quality of this particular state action space. And this expression over here, the RSA plus gamma something, this actually measures the total expected future rewards if you take this action. So if I take a certain action at a certain node, this is the reward that I'm expected to get if I take, like, for all my future state action pairs. However, in this case, we basically created a min-max game where the goal of the attacker is to maximize the reward Q values, and the goal of the defender is to minimize the Q values. And we were hoping that while doing so, we would be able to model unknown adversaries, and the defender would be able to learn policies which is evolved from these unknown adversaries. So this particular thing is called a zero-sum game. What that means is, if for a defender to win, the attacker has to lose, and for the attacker to win, the defender has to lose. Both of them cannot win at the same time. And that's why we have the equal amount of positive and negative rewards. When a defender does an action, the attacker gets the negative of that reward, and when the attacker gets a reward, the defender gets the opposite. Now, I just want to show some of the results that we had. So if we incorporated the knowledge guidance, we actually encounter a lot of non-zero rewards in the initial stages, which helped us guide the model much faster. Now, if you look at the list, left column over here, which does not use any sort of external knowledge guidance, you would see that till a lot of these episodes, less than 10% of the iterations resulted in non-zero rewards. So 90 to 92% of these iterations contain zero rewards, which led the model to learn nothing. But if you have this knowledge injection mechanism, you can actually bring that number way up using some external knowledge and guide this agent in a direction that if you do this, you can expect a higher reward. And a lot of these were unsuccessful, but some of them actually were, which brought the number of non-zero rewards way up. Now, if you look at the average iterations per episode, you can see that with knowledge guidance, we were able to bring that number down. But on the hindsight, we were also seeing a much higher standard deviation, which sort of said that knowledge, all the knowledge may not be very useful. Some of the knowledge can actually, maybe it's actually pushing the agents into learning something that's not very useful, or explore some states which are not very useful. So higher standard deviation is not so great, but if you look at the average number of iterations, it's significantly lower than something that you would see without knowledge guidance. Now, all these experiments were done in simulated, creating with simulated networks. They were all, when we say like online systems, that you are observing the real reward at execution time. When you're executing an action, you would be seeing a reward right then and there. Now, that is not a very realistic scenario if you were to deploy this system in an existing cyber defense scenario, or maybe like in an actual environment, real environment. If you were to deploy this, you would not be able to do this. There are two sets of things. So in online system, what you do is you take an action, you observe the reward right away. In an offline reinforcement learning, what you do is you perform a bunch of different actions, curate this data set, that when you interact with your environment, when you perform a particular cyber action, this is the result that you got, and this is the next state that you discovered, and you take this and create your own training set, and then with that training set, you train your neural network, which can help you learn policies. And this is a more realistic scenario, so it doesn't have to observe the reward during training time or during evaluation time. You just create the data set externally, offline, then you use the neural network to train from this existing data sets. Now, this offline reinforcement learning is extremely useful because in cybersecurity scenarios, you're supposed to observe system variables when you're taking different actions. A lot of them might be extremely risky, and some of them might be just downright unsafe, like you should not be allowed to take those actions. It's kind of like when you're trying to learn a safe driving car, you should not be required to hit a pedestrian to know that it's unsafe to hit a pedestrian. So this is where we use external knowledge, and this is where we also cannot use online reinforcement learning, because in cybersecurity, it's very difficult to define all of those unsafe actions at the same time. So what we did for this experiment, we collected behavioral data from different sources, and we trained our policy on those behavioral data, system behavioral data. Now, this offline reinforcement learning has a significant problem, and we can see that over here. So all these green dots that you see over here, they are the state action pairs which is observed. So notice that in offline reinforcement learning, we interact with this environment, and then we curate a data set, and we are using this data set to train our model. Now, this data set does not contain all possible state action pairs which could have possibly existed. If something was missing in the case of online, you would actually take that action which you haven't seen before. But in offline, you are having to train the system without observing those state action pairs if they're not present in the data set. Now, this green dots that you see are actually the state action pairs which are observed in the training set. Now, when you estimate the Q values, which tell you how good a particular state action pair is, you are more likely to overestimate those state action pairs, even though those unseen state action pairs, even though there is no particular evidence for that. Now, if you think about it, the blue curve is the actual Q value, which is the actual quality of that state action pairs. The orange one is your estimated one, and you're estimating based on data that you haven't seen before. Now, when you do this, you can at some points estimate some of these Q values, which are actually way more estimated than what they should have been. Now, there is this solution which is called conservative Q learning. Now, what this conservative Q learning does is it basically does a conservative estimate for these data points. So these data points are actually called out of distribution data points. And for these out of distribution data points, it basically suppresses the Q values. And that's the whole point of this conservative Q learning. Now, there are a couple of new RIPS papers which say that the CQL is extremely conservative, and just pessimism is just not enough to deal with situations like these. So what we did was, over here, without this term, this beta term, we can see the objective function for this conservative Q learning. So over here, it's actually a minimization problem. So if you think about it, what we are doing here is we are suppressing the Q values for all state action pairs. Okay, so if you have a list of like 10,000 state action pairs, out of which 800 is known and 200 is unknown, you are initially suppressing the Q values for all 10,000 of them. Now, if you have 8,000 sample points for which you actually have the data, you would be increasing this value. So once you see this minimization parameter over here, so what this minimization function is doing, it's actually increasing this negative term, which happens to be the Q values of all the state action pairs, which is coming from the scene distribution. Now, what we did was we added another parameter over here where the state action pairs are something which can be translated from some existing cyber threat intelligence. So for instance, if at some point you are exploring a state action pair and for a particular malware detection task, you can have some sort of an evidence which says that in particular malware X, there is this particular process which has a high number of CPU threads. Now, this knowledge can be translated to this model's state action parameters. And with what we can do over here is, instead of conservatively pushing these values down when there was no evidence for it, we can actually artificially create an evidence from this external CUTI, and we can bring that value up. So notice that if you use CQL estimate, you would end up with a suppressed Q value like this. If this was, let's say, the actual Q value, what it should have been, and if you use a knowledge guided conservative Q estimate, you would end up somewhere over here. So that's the in distribution state actions, and then this is our contribution over here, that it's the state actions which is known to the cyber knowledge graph. And if you change the loss function or the objective function over here, you can end up with better Q estimates for unseen state action pairs. So how do these offline state transitions work? It is basically you start with a state which describes system behavior data, just like I just described before, and the actions could be some of these process names. So this is for some specific malware types where the malwares actually spawn processes, and we are trying to identify which of these processes are actually malicious. So if you look at some of the results, we did get some good results on certain malware families. In others, it was quite difficult to train a reinforcement learning model because of the wide variety in the types of data that's represented by a malware, which brings us to the new challenge about how do we work with novel patterns in data. Now, reinforcement learning did reasonably well in certain types of malware, but in certain types of malware, what we have seen is the data is not very representative, and there is a wide range of how the malware can look like, and there's a huge spread in the, if you just plot the embeddings of the malware, there is a huge spread. So how do we work with novel patterns in data when the data itself is not so representative? So meta learning can work reasonably well, and this is what we are seeing. So if just to give you a brief, a crash course on meta learning right now, what we learn in meta learning is not just the set of parameters which will help you do a certain task really well. We are actually trying to look at a parameter which can be fine-tuned to do any unknown task. So the objective is not to do the best that you can on a particular data set and a particular set of labels. The objective over here is to find a particular model which can be fine-tuned really well into any unseen task. For example, like if you have a particular meta training set and a meta test set, you have a support and query. So that means you're trying to create some tasks. So let's say that you want to distinguish between dogs and lions and cups. That's a task. And then once you learn how to distinguish between a lot of these different types, during test time, you would be asked to distinguish between some unseen classes, and you would be allowed to fine tune your model to a certain number of iterations so that it works well in distinguish those unseen classes. So if you look at this over here, let's say this phi1 star, phi2 star, and phi3 star are some parameters of models which will work well for certain types of malware or certain categories of data. Your goal is not right now to find this parameter which will work well for that specific type of data. Your goal is to find out this intersection point right now. So this intersection point, if you find out a parameter model with parameters equal to this intersection point, it is very fast right now to fine tune with a few number of steps to go to this particular set of parameters, which will work well to any unknown, for any unknown type of data. Now, in other domains, this kind of works well, specifically in the context of zero-shot learning. If you want to do it with meta learning, you could be able to do that in a few shot setting. But if you look at the data, it is actually very representative data. So if you look at all these visual segregation tasks, you are actually starting with data which is very representative. But on the right side, you're looking at the plot of malware data set, which is all over the place. Now, if you want to find out a particular parameter with some very few samples from every unknown class, that class has to have representative data. So this red class over here, if you were to find out a model which will work well by taking a few samples from this red class, you want to ensure that all the samples from the red class are actually representative, which is not the case for malware. So we tried to do a lot of this investigation about what kind of data is actually representative. And we found out that the static and dynamic analysis, if you run the malware for an extremely long time, and if you collect and fuse all the static and dynamic analysis reports, you should be able to get a representation which is fairly representative. So you have to spend a significant amount of time trying to capture a lot of this information about all the static analysis. You have to keep the malware running for a very long period of time, get a huge amount of dynamic analysis reports, system behavior data, all these things together. If you fuse them together, you should be able to get representative data. But then that actually does help, because if you look at our meta learning experiments on detecting these kind of malware, we do get really high accuracy in some cases, but this is only for representative data. You're not expected to have representative data. We can actually be expected to identify malware or benign files based on unrepresentative data as well. So what do we do at that point? Now, this is a new area of research. I'm really interested in doing this, but there's significant challenges associated with that as well. So what typically we do in machine learning is we work with a point estimate. Now, what does that mean? If you are trying to find out a neural network, your output is a set of weights, and specifically a set of values for the weights of the neural network. That's your output. And that's a point estimate. That means you're pinpointing the exact values of the weights, which will work for all data, irrespective of what comes in the test time. Now, that does not work well under uncertainty. What works well under uncertainty is a prior distribution. So if you have to model, or you have to think about modeling a distribution from where you can sample based on what prior information you can have about that malware. So what that means is, if you look at the plot on the left, and if you look at the TSNE plot on the right, it's extremely difficult to sample some specific red dots over here because it's all over the place. The red dots are actually spread across the entire map of the TSNE. But they have some fundamental differences. So they belong to a specific category, but they have some differences, but they also have similarities, because that's why they are being label bucketed into the same category. Now, if that's the case, there are some things that's manifested through the data, and there's something which is not. Now, if we can get that prior information and say that, okay, if you want to detect this type of this red malware, you need to sample a parameter which works well in this space. Whereas if you were to handle from the other side of the same malware category with the red samples, you should be modeling, you should be, sampling a different set of parameters. So the same set of parameters will not work for all the samples for the same malware type. It needs some nuances. So the reason for that is, like, this is our hypothesis, and we did test it out. In other domains, let's say you have 3 different classification tasks. So a set of parameters over here works well for task 1, parameter over here works well for class 2, and parameter over here works well for task 3, which is green. However, in malware, every single malware type is actually a huge spread. And there is a huge overlap between a particular type of malware and a different type of malware. So what do we do in that kind of situations? So if we were to find out a set of weights which work well in identifying a particular type of malware, there is no one location that we can sample the weights from. There is a range of weights that can work well for one particular malware. Now, if that is the case, what do we do with our existing meta-learning approach? Now, if you see the meta-learning approach on the left, we see the basic model-agnostic meta-learning, which is the state-of-the-art for parametric meta-learning. But if you look at the model on the right, which is a Bayesian mammal, which sort of fits a distribution, and then you sample from the distribution to fine-tune it for specific classes. Now, if we can include some prior knowledge and then sample from some specific case, and then sample from some specific locations in your weight distribution, you should be able to find out with a more certainty that this particular weight should work for this type of malware. So the main argument over here is you do not consider all samples from one particular family to be a monolith. There are differences within the family, and then you need some prior information to make that distinction between different samples from the same malware family. So for instance, if this is the distribution of a particular malware family, if you were to detect some samples which is over here, versus if you were to detect samples from the tail of the distribution, you should be seeing some distinct differences in the same malware family. And we are trying to figure out how we can incorporate these differences as part of the loss metric to better this distribution. So what we are saying is, if we start over here, we can actually lead to a better intersection point, which will work well for different malware families. So that's why we are currently looking at Bayesian mammal, and we did get some interesting results with the help of this method. And it's a way of combining 2 different sets of information, basically your malware samples, as well as some prior description of the type of malware that you're trying to detect, and using that information to fine-tune or find a model which can be easily fine-tuned to any unseen class. So one example over here would be if you have different types of malware, if they're distinct, you have some descriptions of these malware types, and you can actually feed it to the loss metric, which internally uses a kernel function, but we can talk about that later, and then optimize that with the help of this prior distribution from where you can sample and then particularly select the type of malware for which you would be optimizing for. So to summarize my talk, what we have discussed is explicit knowledge is important, and we need a combination of the rules that we that we get from external sources, and also the actual data from which we can infer information, and that's the tacit knowledge. And if you can combine this together, that's extremely good for cybersecurity purposes. And for that, we also need timely and reliable external information, because we saw that some of these information were not that helpful in our reinforcement learning exercise. The second thing is, in the reinforcement learning, we know that the RL can actually explore new adversaries. So if you jointly model the adversary and the defender together, it has the potential to model adversaries even before seeing them, because the adversary is jointly learning with the defender. We also saw some experimental results that how we can incorporate external knowledge to reduce the training time of reinforcement learning. And lately, we are seeing how we can extend that to generalize across different types of malware families with the help of meta-learning. So that's the end of my talk. So if there are any questions, I'll be happy to take them right now.
Thanks, Dr. Piplai, for your talk. Please feel free to like ask any questions if you have. Also, I'll in the WebEx, I'll just let anyone, you might need to like raise your hands if you have a question. I'll unmute you and you can ask him directly. Anyone? Any question?
Okay, there's a question which says how to identify out of distribution scenarios. So in out of distribution scenarios are in our context relates to in reinforcement learning setting. Out of distribution scenario is actually any state action pair which you haven't seen in your training set. So for example, like if you try to collect the data for all sorts of system parameters and the processes that execute, if there's an unknown process or unknown variation of system process, it's considered out of distribution because it's not something that you have encountered in the training set. However, if you're talking about out of distribution malware, that's a different area of research. There are a lot of work which looks at the embedding space of the malware. There are distance-based measures which people can use, and there's like detecting out of distribution cybersecurity malware is like another area of research, and that will probably take another hour of talk to describe.
I hope that answers your question. And we have our Dr. Piplai. We have one question from here. Charles, you can go ahead.
Hey, Dr. Piplai, thank you for the presentation. My name is Charles. I'm a PhD student, and I just have one question about the format of the reinforcement learning policy.
Mm-hmm.
So typically, state action pairs, as I've seen them in RL, are typically in discrete space, but in the cyberspace, it seems like there's just a continuous space of state and action. So how do you discretize that state space and action space for your RL policy?
So for our experiments, actually the action spaces were discrete. However, there were in the simulated environment, the action spaces, if you remember, were like launching an exploit. So for example, like if you are a particular node, then you are launching an exploit from node I to node J, right? So that is, if you have like 10 or 20 nodes in the system, it will have like an action space of 10 choice 2. So that's how, like, it's a discrete space, and every single action is actually mapped to a specific type of action or a specific exploit that you're launching from one node to another. However, there are other applications where I personally haven't worked on them, but there are other applications where you would need to have continuous continuous action spaces. And for that, I think like there are multiple discretization techniques, like maybe bucketizations. There are things, there are bucketization strategies that you could use to deal with that problem. But yeah, that's a very interesting question. Fortunately, in my case, I did not encounter that situation. But if you are facing that problem, I'll be happy to talk to you offline.
Thank you.
Anyone else with any questions? I know that was intense a bit, so please feel free to like reach out to him, like if you have any questions, or you can directly shoot him an email.
Mm-hmm.
Also, if you want to revise this video, this is going to be on YouTube, so you can look at it over and over again, because there are a lot of maths, and I know for our undergrads, you can. So we are already recording everything. So anyone else? Otherwise, we'll let Dr. Piplai off for a weekend, I guess. Mm-hmm. Thanks, Dr. Piplai. Thanks again for accepting our offer. Please, like.
Thanks a lot for having me. It was great talking to you. And yeah. If you want to talk to me offline, you can talk to Shashwata. Like, we can definitely have a meeting. Specifically, if you're facing with reinforcement learning problems, I'll be very happy to help.
Sure.
Thank you.
Thanks, Dr. Piplai. Thanks, Dr. Mittal, and thanks everyone joining online and offline here.